And we're back. Welcome back and happy Thursday. Today, we will pivot our focus to inference, the drawing of general statements about the population based on functions or statistics you compute over samples from that population. But before we begin, some administrative bits. The reading in Chapter 9 of the main text is Chapter 9. Project number 3, again, has been on the blackboard from last week. It is due this Friday, the 19th of March at 8 p.m. sharp. Reminder, this is 8 p.m. and not 11:59 and 59 seconds. So please make sure to mark your calendars, your smartphone, whatever device you use or instrument to remember. All right. So when we last left off, we talked about implementation of the PLA algorithm, and this PLA algorithm searches through the set of hypotheses, their weight vectors, looking for that final best hypothesis that most closely mimics the labeling action of the unknown target function. And you can think of this search as moving the decision boundary in order to correct for a misclassified point. All right, so let's look into the beginnings of inference. So if I use this word stability, what does that conjure up for you? Stability, something is stable. Well, pictures like this. This bridge is stable, it's solid, it's in place, it does not move. This tightrope walker, it's a different type of stability. Yeah, it moves, but it doesn't move too much, and it allows you to stay upright. So when you think about stability, you think of two things. You think about reliability. You can do it again and again and again. It might move a little bit, but on average, you stay upright, firmly established, like that bridge. It is a rock. It's not going anyplace. And so with this reliability, what comes to mind is this idea that something is not likely to fail. Firmly established, this doesn't change very much, doesn't move at all. You can count on it because it doesn't change very much, like that bridge. So when we talk about reliability, not likely to fail, that's kind of like our proof for unbiasedness, that litmus test that we had for estimators or statistics over a sample, over data. And firmly established, it does not budge, doesn't change much. That's like consistency. The probability that your estimator diverges from your unknown population parameter gets smaller and smaller as you increase the size of that sample. It's not going to move very much. And so for this reliability, this unbiasedness, you can give it all kinds of data. You can give it typical values, you can give it outliers, and if you measure this from samples again and again and again enough times, on average, i.e. in expectation, it's exactly this unknown population parameter that you are striving for. So that's one way of talking about this good replacement. And with consistency, we said that if you give it enough data, it's always very close to its faithful description of this population parameter. And so these two ideas, the unbiasedness test and the consistency test, we said that if an estimator satisfies both of them, that it is a wonderful replacement for this population parameter, which at the end of the day, you don't know what it is. And so for unbiasedness, we said if you have some sample of size n, and they are, quote-unquote, IID, independent and identically distributed, so one sample does not influence the other, and they're from the same distribution. So if you have some estimator theta hat derived from a statistic, a function over that sample, we have that the expectation of that theta hat, or estimator, or statistic, is exactly equal to this unknown population parameter theta. And this also played out in a MATLAB example that we demonstrated earlier in the semester. And so if your estimator is S squared, the sample variance, well, we said the sample variance is an estimator for the population variance, sigma squared. So that means, by direct proof, which is true, Remember, this sample variance has 1 over n minus 1 as the leading coefficient. If we take the expectation of this sample variance, we get exactly sigma squared, and we can do this by direct proof. Likewise, if our statistic, our function over the data over a sample, is x bar the sample mean, we said it's an estimator, a good replacement for mu, the unknown population parameter, the population mean. And we take the expectation of x bar, and we can show that it's equal to mu, our population parameter, and we can do that by direct proof. Likewise, when we talked about consistency, we said we have some estimator theta hat, and then you have that the probability that theta hat diverges from or is different from this unknown population parameter theta by more than some error tolerance epsilon, that probability goes to 0 as you increase the sample size, as n goes to infinity. If your theta hat, your estimator, is a sample variance s squared, you can show this by demonstrating in the limit as n goes to infinity, the sample size gets bigger, that this s squared is exactly equal to theta squared. And if s squared is exactly equal to theta squared, sigma squared I mean, if s squared is exactly equal to sigma squared in the limit, then the probability that you're going to diverge is going to be exactly 0, because if our s squared is sigma squared, you're going to have 0 probability that 0 difference is greater than epsilon. It's exactly equal to 0 because it's always 0 if s squared is equal to sigma squared. All right. So if our estimator theta hat is x bar, the sample mean, and we said that this theta hat x bar, this estimator, is an estimator for mu, it's a good replacement, we can show that in the limit, as you increase the sample size n to infinity, n goes to infinity, that this x bar is exactly equal to the mean mu, population mean. And so in the limit, we have that difference. It's always 0, so the probability that it exceeds epsilon is going to be exactly 0 because it never is greater than epsilon if it is 0. And so that's how these proofs play out for our sample mean x bar and our sample variance s squared. So let's look at what is this inference idea. And so we have, recall, a population, and we looked at an example concerning a theoretical example for the homeless population, and we said this is a hierarchical population, and that was our working assumption. It's a simplified assumption. And we said it consisted of 4 main subgroups: homeless veterans, families, those who are drug addicted, struggling with drug addiction, and aged out foster children. And so we said that we have floating around in this population 4 population parameters, ground truth, theta 1, theta 2, theta 3, and theta 4. And we don't really know what they are, but through samples, you can compute a statistic that are reasonable replacements for these unknown parameters. And these are estimators theta 1 hat, theta 2 hat, theta 3 hat, and theta 4 hat. So theta 1 hat is the replacement for theta 1, theta 2 hat is a replacement for theta 2, and likewise, up to including theta 4 hat is a replacement for theta 4. So that means if these estimators are stable, they're reasonable replacements, both unbiased and consistent. Remember, we want to be able to make statements using these estimators, things we do know from the data, that hopefully these statements apply to this unknown population. And this is going to save us time, money, and effort, because even for a town the size of Dover, 37,000 people roughly, you'll never be able to find out with absolute precision all of the homeless population. So instead of dealing with the population, you're dealing with these estimators, these theta hats, for each one of these subgroups for your population. And so I think this was pretty amazing. I remember the first time I learned this, I thought, oh, wow, that's quite amazing. That just by doing things the quote-unquote right way, what you do know from the data, our theta hats, will apply well to what you don't know about this population, all of these theta values. It's pretty amazing. And so suppose, for example, you're dealing with customers that arrive at a store. Do you know about the rate at which customers will come into the store? I don't. If you do, maybe you should buy a lottery ticket. But that being said, let's imagine then we instrument our store, our retail concern, and we put an overhead camera inside, viewing the entry box, and we're just tracking the number of people who enter the store and leave the store. Now, keep in mind that we're not looking at identities. We're just tracking whether someone goes from outside to inside through the entry box of the store or from inside to outside. And one of the things you'll notice if you direct your attention to the upper right-hand corner of this video, you'll see the number of entering increments and the number of leaving increments as well. And of course, if you subtract the number leaving from the number entering, that's the number of people in the store. So at any given moment in time, you can tell how many people are in the store. You associate that with your register, and you can compute literally the rate of revenue that your enterprise collects. Now, of course, you don't know ground truth what that rate is. So we're going to model this and assume it's a Poisson distribution, which is a good model for events in time. So recall from last semester, we have a Poisson. It's the discrete distribution because it's countably infinite. And lambda, our rate, is going to be the average number of observations over standard modules of observation, delta t. Now, we did the derivations of the mean and expectation for the Poisson, and the mean is lambda, and the variance is also lambda. So this Poisson distribution is different from all the other distributions in that its mean and its variance are both this lambda. And so we take this Poisson, and let's say we make an observation. We know that the sample mean is a stable estimator for the population mean because it's both unbiased and it's also consistent. So that being the case, everywhere we see the mean of the Poisson distribution, lambda is the mean, we can replace it very confidently with x bar. And we can now take this x bar from these measurements like this overhead camera system and just take that x bar for module of observation, some window of time, maybe every 5 minutes, every 2 minutes, count the number of people that arrive into the store every 5 minutes, and then compute x bar. And now we can substitute for this unknown population lambda, population parameter lambda. So doing that, we now have an expression for the probability associated with the number of customers being in the store at a given time, or module of observation, and we can now sample from this. Now, of course, if we sample from this, now we can answer all sorts of interesting questions. Is it typical for 20 customers to walk into the store? How much revenue can I expect to collect? That's just the probability of a certain number of customers, and then we multiply by the average amount of money that these customers spend, which you can absolutely get from the register information. How many employees can I afford? Well, it depends on your revenue. If your employee count can't support the revenue, then you're not going to make any profit, and the store has to stay in business. And so you can use this method of substituting a statistic, an estimator, for the unknown population parameter, provided that it is a good stable replacement, i.e. it's unbiased and it is also consistent. Now, of course, if it's not unbiased or it's not consistent, knowing so would give you some information about how to remedy the situation, you can fix things up. All right. So let's take a look at an approach. And we said instead of looking at the population, you're going to deal with the estimators, the statistics. And there's one method called the method of moments approach, and it is a recipe of sorts for how you arrive upon stable statistics, rather than just having to come up with a statistic and then doing the proof for unbiasedness and consistency. Statisticians over time have done the work to come up with methods that guarantee that the result will always be stable. And so what you do in method of moments is you find good substitutes or good estimators by equating something called the population moment with the sample moment and then solving the equations that you get, system of equations, when you equate the population moment with the sample moment. Okay, but that just begets a question. What exactly then is a moment? Well, in a moment, no pun intended, we'll talk about it. And so there are many songs throughout history about moments. This particular one, for the sake of copyright issues on YouTube, I'm not going to play it. But nonetheless, it's at this moment, and music can tell you a lot, I think, about statistics. But that being said, what is a moment? Now, when all of this was being developed, well, physics was already in play, and the statisticians reused tools from physics. And in physics, a moment is a combination of a physical quantity, a force, at some distance. And what this moment does, it allows you to force multiply, if you will, to amplify the amount of force that you're using to do something. And so here we have a pivot and we have a wrench. You apply a force of 50 newtons. You can multiply that force proportional to the length of that wrench, that tool, to give you a greater turning force or torque experienced at this pivot. And that's a lot more force than you could generate with your hand trying to turn that pivot. And so it's a force multiplier. It's force at a distance. And so why do we care? Well, when we balance things, or let's say you have an automobile and you're trying to jack up the car to change the tire, well, you don't have the strength to lift a heavy car, but with the right type of lever arm and the right type of force and pivot point, you can actually generate that force. Now here we have a pivot point, and we have on the right-hand side, we have a 20 Newton force 1 meter away, so it exerts a force of 1 Newton meter. That's the 20 newtons of force in the downward direction times the 1 meter, which is the distance from the pivot for this force. And then we also, on the left-hand side, have a force, but it's only 10 newtons. It's half of the force. Now, this 10 newtons is 2 meters away from the pivot. And it just so happens that the moment for each of these is equal. You have 20 newton meters for the weight on the left, and you have 20 newton meters for the weight on the right. And so with less effort pushing down on the left-hand side, you can generate the same force. And this will give us a balance because the sum of the moments is 0. You have the moment on the left wants to bring the board down in that direction, and the moment on the right wants to bring the board down in that direction. If the moments cancel, well, you're going to balance. You're going to balance. All right. So this exercise, or rather this video, is an example, clever example, but it's all physics and explains what you can do with moments. And again, due to copyright issues, I'm not going to show it on YouTube. But let's see what a moment is. In statistics, and again, statisticians reuse the tools of physics in order to describe moments. Now, in statistics, the purpose of a moment is to describe the shape of a distribution. And you can think of a distribution as a set of so-called mass points. And so here we have a distribution on the horizontal axis. We have all of the so-called support set. Those are all the values over which probabilities are defined. You could call that the domain of the probability. And then on the vertical axis, we have the probability itself. And so x3 has a higher probability than x1. Now you think of these probabilities as having a mass of a certain size. And so this point has a mass equal to its probability. That point, x3's probability, has a mass, and it's a bigger mass than the mass associated with x1. And so as a mass, well, gravity acts on masses and it exerts a force, and that force is the weight that you perceive for that particular mass. The bigger the mass, the bigger the weight. And gravity acts on each of these probabilities, so-called mass points, with a force that exerts downward. And so you can imagine if you have a larger mass, like x3's probability mass, there's going to be a longer arc length or longer arrow connoting the fact that it's a larger force. Now, you can select a pivot like a seesaw, and if you put this pivot at a point, well, if there's more mass on one side of the pivot than the other on this seesaw board, it's going to pivot downward in that direction, or it's going to pivot downward in the other direction. And so this point, that's the median, right? It's the middle of these values in order, okay? But you can also compute a value by adding up the moments, the forces times the distances from a pivot point. Now, of course, there's a special such pivot point such that if you place the pivot in a certain location, this board, given all these forces, these weights associated with these moments, it's going to balance. That plank, that seesaw is going to balance. Now, this balance achieving pivot point has a name. That's the mean. And so sometimes the mean, mu, is called the center of mass because it's the center of where you get this balance, where all the masses, some of the moments equals zero, center of the mass for your system. And so the mean is where you have center of mass, or the point where the sum of the moments is equal to zero, because these forces want to pull in one direction or in the other direction. All right, so let's go back to the values computed by adding up the moments. So if we add up those values, all these x's, and we sum them together, and we put them together, we have some sum. So if we add up all these points, all these xi's, well, we have a little bit of problem. So what is that problem? Well, the problem is that some of these values are bigger and some of these values are smaller. So we need a reference point. Now, of course, if we shift or add a scalar to these, now we're going to get a different value. So if we shift the distribution 2 units to the right, we get an entirely different value for the sum, and that means the moment, it changes based on these values. And so that means our measurement of shape of the distribution is going to be off when we have this shift. And so how do we fix this? We want to make the center of this distribution is in a standard way. We place it at origin. And how do we place it at origin? We shift it. We shift it by subtracting the sample mean from each of these values. So now each of these original xi's has a new value, which is its old value xi minus x bar, the sample mean. And this has the effect, let me flip back and forth, of shifting the origin from where it was to be at the center, the natural center, this mean. And so we're centering the mean, so to speak, about origin. So we're bringing the mean, the center of mass, to change it to be the origin when we subtract the sample mean x bar from each data point. So now if we do that, we don't care about whether a point value is greater than or less than this new center, our center of mass. We care about the magnitude. So we're going to square this difference. And we square this difference, we generalize it with the sum or integral, depending on if it's discrete or continuous distribution. We take each point, subtract from it the pivot, our center. We raise it to a power arbitrarily n, and then we multiply by the force. So here we have the force times the distance, and that distance is raised to a power. And this is the so-called nth moment, which is the generalization of the moment, which derives from physics. All right, so we center on origin. C is equal to the mean. It could be x bar. And its centered balance point, meaning if it's not centered, C is equal to 0. All right, and so in summary, we have the first moment, which is the mean, n is 1. The second moment, center, is the variance. The third moment is skew, which measures the lopsidedness. And the fourth moment is kurtosis, which measures the Gaussianity or the flatness of a distribution. And each of these moments talk about the shape of the distribution, and the higher order moments talk about more esoteric, complicated shapes. And this is how you describe in statistics, generally, the gross level shape of a distribution. So with that, we'll end there. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.